Hey everyone, in a previous video I discussed can gradient descent be applied to non-convex function, and the answer to which is yes, but with some caveats. And I discussed when applied to a convex function, gradient descent is guaranteed to converge to the global minimum. However, for non-convex functions, there may be multiple local minima and saddle points which can make convergence to the global minimum difficult or not guaranteed. Now, fundamentally, why some machine learning problems does not have a global minima, or why they have a non-convex curve on which regular gradient descent algorithm cannot be applied, or the application is not guaranteed to produce the desired result. Now, there are a few reasons for that. Number one, nonlinear relationships. Real-world data often exhibit nonlinear relationships between input features and output variables. When we try to model these relationships using machine learning algorithms, the loss function, which measures the difference between the model's predictions and the true output, can become highly nonlinear and non-convex. This means that there may be multiple local minima, saddle points, or flat regions in the loss landscape. Number two reason is overfitting. Complex models with many parameters, for example, in a really deep neural network, can fit the training data very closely, potentially capturing noise in the data. This can result in a highly non-convex loss landscape with many local minima corresponding to overfitted solutions. And regular gradient descent algorithm may get stuck in those local minima, leading to poor generalization performance on new data. Point 3 is regularization. Regularization technique like L1 or L2 regularization are used to penalize certain model parameters if they have large values. This can help prevent overfitting and improve generalization performance. However, regularization also make the optimization problem more non-convex, as it adds additional terms to the loss function that may not be smooth or have easily computable gradients. And now the next question is how to find global minima in cases where gradient descent does not work because of the non-convex function. So many non-convex problems can actually reach global minima, albeit with some amounts of regularization. For example, the Reitinger flow algorithm can solve phase retrieval, a non-convex problem. There are also gradient-free optimization algorithm like the Nelder-Mead method, or CMAES, which stands for Covariance Matrix Adaptation Evolution Strategy, which do not rely on gradients and can be used to optimize non-differentiable or non-convex function. Then there are Bayesian optimization. This model builds a probabilistic model of the objective function using Gaussian process or similar surrogate models. It then iteratively chooses the next point to evaluate by balancing exploration, searching in uncertain regions, and exploitation, that is searching around the best known solution. This approach can be more sample efficient than other global optimization methods. And further solution, random restarts, which performs gradient descent with multiple random initial points. This increases the probability of finding the global minimum by exploiting different regions of the search space. Then we have simulated annealing. Inspired by the annealing process in metallurgy, this algorithm starts with a high temperature that allows for larger random jumps in the search space. As the temperature decreases, the jumps become smaller, allowing algorithm to fine-tune its search around potential minima. This method is more likely to escape local minima than gradient descent. And the next one we have in this kind of situation, that is finding the global minima for non-convex function. We have particle swarm optimization. This is a population-based optimization technique where each individual particle represents a potential solution. Particles move through the search space based on their own and their neighbors' best known positions, eventually converging towards the global minima.